The 100 gigabit per second Ethernet project gave us the opportunity to carry out the first real integration between the networks laboratory, where the traffic is managed up to the IP level, and the All Optical Technologies laboratory, where the signal is processed at the physical layer in the optical domain. The aim was overcoming the electric bandwidth limits and guarantee ultrafast and flexible communication systems. For this experiment, we used video traffic generated at 10 megabit per second by an open source application server, named VideoLAN server, running on a Linux PC. The 10 megabit per second signal is processed by a Juniper router that aggregates different data flows and provides a 1.25 gigabit per second Ethernet optical channel at 1300 nanometers. Then 8 replicas of the channel generated at 1.25 gigabit per second are transferred in the All Optical Technologies laboratory, where an Ericsson Muxponder receives the 8 data streams and aggregates them in the electrical domain by exploiting the time division multiplexing technique. In this way, a 10 gigabit per second Ethernet signal is generated. The 10 gigabit per second Ethernet traffic is then optically managed in order to obtain a 100 gigabit per second solution. By exploiting the facilities and the expertise in the Integrated Research Center for Photonic Networks and Technologies, we implemented a 100 gigabit per second Ethernet experiment based on optical time division multiplexing and polarization diversity. First of all, a non-return to zero converter block is needed. Then, an OTDM multiplexer based on delays in optical fiber allows aggregating 5 channels at 10 gigabit per second. And finally, 2 replicas of the 50 gigabit per second OTDM signal are polarization multiplexed by means of a polarization beam combiner. In this way, the 100 gigabit per second Ethernet traffic is obtained. The NRZ to RZ converter is an inverting data scheme based on cross-gain modulation in an SOA. At the receiver, the 100 gigabit per second Ethernet data stream is polarization demultiplexed by means of a polarization beam splitter. And then, the 50 gigabit per second OTDM frame is demultiplexed exploiting for remixing in fiber. A second stage regenerates the extracted channel before the electrical receiver by means of cross-gain modulation in an SOA. This inverting block allows also to recover the original data logic. The optimization of the demultiplexer in terms of polarization and synchronization is the most critical aspect of the experiment, mainly due to the absence of the clock recovery. A bad choice of the demultiplexer parameters induces a degradation of the received eye diagram up to a complete closing. In this case, the number of errors at the receiver increases too much to be corrected by the forward error correction, and the transmission is lost. On the other hand, a good setting of the demultiplexer with an optimization of the polarization state of the received signal and with the correct position of the pump used in the OTDM demultiplexing stage allows obtaining a well-opened eye diagram with a considerable reduction of the errors at the receiver. In this situation, the forward error correction is able to correct all the errors and to maintain a high-quality transmission. In this experiment, we have been able to transmit the 100 gigabit per second Ethernet traffic over a 1.4 km long span of dispersion-shifted fiber, which corresponds to a total chromatic dispersion of 0.9 picosecond per nanometer. The main limitation has been represented by the high jitter of the clock, used in the Ericsson Muxponder to generate the 10 gigabit per second Ethernet signal, and to the absence of the clock recovery in the OTDM demultiplexer. Nevertheless, this first 100 gigabit per second Ethernet experiment, which exploits real traffic and commercial systems to generate the 10 gigabit per second Ethernet frames, represents a first step toward the demonstration that the all-optical signal processing can be really introduced in the next generation broadband and flexible optical networks.